So our next speaker is Nguyen from the United States Naval Academy. She will speak on deformations of quantum groups.
Thank you, Karen, and thanks to the organizer for inviting me, and thanks everyone for attending the talk. So I guess my talk will have a different flavors from all the previous ones. I'm more going to be talking about the structure of the algebras, or in this particular case, the quantum groups. So as a generalization of like Hopf algebra, bialgebra, things like that. And then see the relation that it has with the co-module or the module categories of this quantum groups. So this is joint work with Hongdi Huang, Charlotte Ken Vashaw, Padmini Veerapen, and Xingting Wang. So first, I'm going to give some basic background and motivations. I'm going to talk about two different kinds of deformations, or in our paper, we actually call that twisting or twisted algebras. So the first kind of twisted algebra, again, everything is going to be over some base field. It doesn't matter the characteristic. It doesn't matter whether it's algebraically closed. And tensor product will be over K unless notified otherwise. So the first kind of deformation I'm talking about is two co-cycle twist. And this is done on a Hopf algebra. So let's recall that I have H as a Hopf algebra if it has the algebra structure. So it has a multiplication and a unit map structure. And it also has a co-algebra structure. So these two structures are compatible that make it become a bi-algebra. And to make it a Hopf algebra, we have the existence of an antipode map S. So here throughout the talk, I'm going to use the co-multiplication, the delta is mapping H to a summation of H1 times H2. So this is what we call the Sweetler notation. So some basic example of Hopf algebras that we've seen are the group algebra over any finite or infinite group, depending whether you talk about finite or infinite dimensional Hopf algebra, or just a polynomial algebra, polynomial rings, or universal enveloping algebra of a Lie algebra, or small quantum group or quantum groups. So on this Hopf algebra, I'm going to let sigma to be a two co-cycle is basically an element in the Hom K of H tensor H into K, the base field. It is a convolution invertible linear map that satisfies these conditions. I'm not going to explain what they are, but there's x1, x2, those are coming from the Sweetler notations. You apply that has some condition with the co-multiplication map. In fact, this two co-cycles actually can be computed coming from the Hochschild cohomology, which I might maybe in Maria Julia talks, she's going to hear that again. So on this, using this two co-cycle sigma, I'm going to define the two co-cycle twist or deformation. H sigma, it basically have the same co-algebra structure as H, but we deform the algebra structure. We deform the multiplication using this formula, so using sigma, right? So a result that done by Doi and Takuchi in '93, showing that this H sigma is again a Hopf algebra. So it has a Hopf structure, it's a bialgebra, and the antipode map is given explicitly as well. And moreover, the category of co-module of H is actually equivalent to the category co-module of H sigma using as a tensor category. So it has a monoidal structure and so on. So it's behaved under this the tensor product. Right, so that's the first kind of deformation of Hopf algebra. And the second kind of deformation that I would like to talk about is done on graded algebra. So it has no Hopf structure, just on a graded algebra A. I'm going to take a graded automorphism, phi, and then define A phi to be just A as a vector space with a deformed product is given by phi. Right, so here all my S and R are homogeneous element using this grading. And then this is what we call the right Jang twist. And similarly, you also have the left Jang twist done similarly as well. In fact, this kind of twisting is first introduced by Artin, Artin, Tate, and Vandenberg. But the reason we call this Jang twist is because due to the result by Zhang in 96, he showed that the A phi is again a graded associated algebra. And moreover, there's also the equivalence between the two categories of graded modules of A and that of A phi. Right. So because of this equivalence, many of the algebraic properties is actually preserved under the Zhang twist. So for example, Gelfand-Kirchhoff dimensions, global dimensions, the X algebra, Altenschalter regularity, and so on. So in fact, some of that feature is actually being used to classify AS regular algebra, and this is still an ongoing project. All right. All right, so those are the two kinds of algebra that we've seen. So let's just look at the big picture or summarize again. So we have two kinds of deformation or twisted algebra. One is twisted by two co-cycle twist that's done on a Hopf algebra using the two co-cycle sigma. The other one is Zhang twist is done by a graded algebra and twisted by the graded automorphism. And we've seen the equivalence between the modules or co-module categories here. Right, so a natural question for us to ask is, how does these two deformations are related? Right, so here, because Zhang twist is done by grading, so I have to assume starting out, if I have a Z-graded Hopf algebra, right, can a Zhang twist H phi can be realized or associated to a two co-cycle twist H sigma for some particular two co-cycle sigma. Right. So to answer that question, we're gonna talk about the main result and then tackle two basic questions first. So the first question is, does Zhang twist here, when it's done on graded algebra, it does not have a Hopf structure, right? So the first question we want to ask is, what is the condition when can the Zhang twist of a Hopf algebra H again have the Hopf algebra structure or bi-algebra structure first to begin with, right? Then we can now talk about, how is it related to H sigma. So the question B is, when can a Zhang twist be realized or be associated to a two co-cycle twist? So to tackle question A, we define or introduce a twisting condition on a bi-algebra for generality, but of course it can be done for Hopf algebra. That the first condition is just assume that is Z-graded. And the second condition basically is saying that the co-multiplication sort of preserve the grading of this bi-algebra, right? And we show that under this, if a bi-algebra satisfies the twisting condition, or in particular the Hopf algebra satisfies the twisting condition, then when we take the Zhang twist, this Zhang twist still satisfies the twisting condition, and it is again a Hopf algebra, right? So that's answer to question A. I'm not going to the detail about the proofs, but that's basically the idea. So this condition is quite useful. And to answer question B, we then look at giving another notion that's called twisting pair. So a twisting pair is just a pair of algebra automorphism that satisfy these two conditions that basically nicely behave with respect to the co-multiplications and the co-unit map of a bi-algebra, right? So on this twisting pair, we have these main theorems here that if we have a Hopf algebra that satisfies the twisting condition, again, this means that it's guaranteed that the Zhang twist of H is again a Hopf algebra, right? And then if I let phi1, phi2 to be a twisting pair, then for the first result, we can actually describe explicitly a linear map sigma and then prove from H tends to H to K that has this kind of a formula that we can prove that it's actually satisfied the condition to be a two co-cycle on H. Right? And then the second result is actually answering our question B, is that with this two co-cycle, with this sigma that we define in part A, the two co-cycle twist is actually can be proved is isomorphic to the Zhang twist of actually phi1 composed to phi2. So again, this phi1 composed to phi2 is again a graded automorphism, right? So this is the Zhang twist, right? So the consequence of this result is that the H and this Zhang twist here are Morita-Takeuchi equivalent. So that means that the category of co-modules over these two algebra tensor or monodally equivalents. So that's basically target the main question that we started out with. But there's more result that we've done in this paper. So one of the advantage for this approach that
you have about 1 minute left.
Yeah, sure. Yeah, is that the twisting pair are straightforward to compute, so it's easier than computing the two co-cycle. And due to the equivalence of the category that we've seen before, that many algebraic invariants are actually preserved under the two co-cycle test. So that's the next result that we did in our paper, is that we look at study the property as well as computing or classifying all the twisting pair for various classes of Hopf algebra. And so for the interest of time, I'm gonna just give this kind of summaries here. We look at twisting of two types, the Jiang twist and the two co-cycle twist. So the next question of future work that could have been that we've been twisting the algebra structure. So what about twisting the co-algebra structure? Is there such a notion as a co-Jiang twist? Or, and the reason, the motivation for us to asking that question is the sort of the dual version of the two co-cycle twist is the Drinfeld twist, right? So that's the motivation for maybe future projects or something. All right, thank you for your attention, and I'll end the talk here.